Well, thanks very much, Mark, and just to repeat his welcome to Durham. This is the talk I'd like to present. It's split into 4 parts. We're going to start by looking at superconducting materials and the applications that superconducting materials are used in, and then have a look through the course and just see what you'll do in the next 2.5 days. This is the guts of the talk here, where we're going to talk about the critical current measurement, which is the central measurement that you're going to try to complete in the 2.5 days here. And this is a practical course, so you'll be split up into various groups of 2 to start with today, and then when we come to do measurements in high fields at low temperatures, you'll be in groups of 4. And it's very important that you try and make sure that everyone in the team has takes some time to do the measurement themselves. This is not a course where you just sit in lectures and take notes and try and remember things. God alone knows how the memory works and how you remember the sorts of things that you all did well at as undergraduates. But another way to imprint these things in your mind is to actually do them. And this course is about that. So please make sure that if you're in a group with a more reticent student, that everyone has a go and everyone solders up some samples and everyone has a go running the measurements. So in the second part of the talk, we're going to look at exactly what this measurement is. And although I'm not going to go into the basics of why materials are superconducting, I'm hoping to explain as best I can what's going on during this measurement, so that you've got some idea about, while you're taking the measurement, what's going on inside the material itself. One of the big changes that we're making in moving, in the UK at least, in moving from jet to step, is to move from a copper technology to a technology where we're using superconducting materials. And one of the important things for students coming through the CDT is that no matter what role they may take in fusion, if they stay in fusion, we want you to feel that you've got a good understanding of this superconducting machine. We have engineers who are building or making decisions about these machines that have had very little training in superconductivity, and we don't want that in the generation that's going to take this project on. So this is the idea. This is probably the most important parameter. The reason that we use superconducting materials, this ability to this critical current that you're going to measure, and we want to make sure that you've got some idea of the science or the physics of what's going on when this measurement's being made. And then in the third part of the talk, we're going to look at not just the superconducting material that we currently intend using in STEP, but at all the industrial superconducting materials, look at the lectures, and then we're going to have a discussion at the end. So let's kick off through the 4 parts of this talk. First of all, we can look at the applications that use superconducting materials at the moment. Superconductivity has these main applications. There are MRI body scanners, so that in the hospital down the road, we've got a body scanner that looks something like this. This is a $1 billion industry. About half the MRI magnets in the world are made in the UK. Then we've got transport. There are these levitating trains. We'll look at that in just a moment. Another big application for superconductivity is high energy physics. So of course we've got CERN, where all the magnets are superconducting magnets. And then the last big application that certainly we're hoping for, and is using a lot of superconducting materials at the moment, is fusion. And possible future applications include power transmission, maybe rolling out of fusion, and rotating machinery. But these applications here, these already use superconducting materials, and we'll just have a quick look at those. So there are the standard body scanners that, as I mentioned, are in many of the hospitals around the UK. These allow you to see tissue non-invasively, but there's also research going on in superconducting materials in so-called functional magnetic resonance imaging. And in this case, we can start to look at what's going on inside the brain. The state of the art is a lab just outside Paris in Saclay with a high field of 11.7 Tesla. And we can look at which parts of the brain are being activated in various different types of activity. So in some cases, if you ask somebody to look at faces or pictures, or you ask them to say words, we can see which parts of the brain are activated. And of course, this is part of the attempt to try and understand things like Alzheimer's disease or bipolar disorder and so on. As I've mentioned, the UK fabricates more than 1/2 of the superconducting MRI magnets. And if you want to work in this field, of course, we need world-class high-field superconductivity. That's what we're going to hope to look at in this lecture here. We need to understand world-class cryogenics, because the superconducting magnets inevitably run at low temperatures, and that's lecture 2. And we also need world-class magnet design and quench control. So the second lecture on cryogenics will be this afternoon with Charles Munro, and the lecture on magnet design and quench control, which is one of the properties specific to superconducting materials, will be covered tomorrow by Alex Blair. There are other applications for superconducting materials. There's the so-called Tokyo-Nagoya maglev train that's being built, travelling at about 500 kilometres an hour. It's 250 kilometres of tunnels, and I'm not sure exactly when it's going to be delivered. They originally spoke about 2027. Please come up. Yeah, don't worry. They originally talked about this being in 2027, but we'll see exactly when it comes online. And just to say that in 60 years of operation, Japan has had no serious accidents in their maglev trains. If we want to think about this as a technology, again, we need these 3 things here, and there are lectures on these things here. But as I say, one of the important things about this the course here in Durham is to do some practical measurements of the most important property. Now, of course, you know about the CERN particle accelerator and the discovery of the Higgs boson. What you may not be aware of is that there was an explosion inside the CERN accelerator in 2008. It took about a year for the repairs to be done and for the system to come back online. I don't know what the cost, the equivalent cost would be for a system like this being down for a year. But this is about understanding that a superconducting magnet is not the same as a copper magnet. That there are some properties specific to superconductivity that you need to understand in order to make sure that this sort of thing doesn't happen. In terms of the mission at CERN, of course, they're trying to do world-class research at the forefront of human knowledge. They're building scientific teams from all over the world, and they're training next generation of physicists, engineers and technicians. And these are the sorts of aims for fusion as well, with these large projects. And if we want to understand or work in an area like this, which of course is also open, you need to understand high-field superconductivity, cryogenics and magnetism. And I saw this, or we were made aware of this relatively recently. This is Japan launching a fusion tokamak. And in this case, you can see that it's been launched quite recently, and they're hoping to have a demonstrator in mid-35 or 40. And in this case, again, we need to understand the superconductivity that we'll look at in this lecture. We need to understand cryogenics that Charles will look at, magnet design that Alex will look at, and we also need to understand HDS cables and magnets. And so I hope by Wednesday, when Stuart gives his talk on HDS magnets, you can see how to go from the sort of measurements that you're going to do on tapes, superconducting tapes, and how that can build up. That's the basic building block for an HDS cable or magnet. So this is the core of the measurement that we would like you to do. In principle, it's a very straightforward measurement. You could see it, for example, as a non-linear Ohm's law. So here we've got voltage on this axis here, and we've got current on this axis here, and you can see that as we increase the current, the voltage stays at zero, hence the name superconductor. And eventually, when we get to a high enough current, we reach something that's called the critical current, and then the voltage just takes off. In this case, we've done the measurement in liquid helium at 4.2 Kelvin and in a field of 7 Tesla. And we've got a very low, very nice baseline and very low noise. This measurement is beautifully done. And you can see that this here is the critical property. That means that rather than putting a power station on the side of CERN, for example, and driving these magnets with copper, it's cheaper to pay for the cryogenics that cools the magnets at CERN down to low temperatures, and then run with magnets that have essentially zero resistance. But you can see they don't have zero resistance for all possible currents. In this case, the superconductor can carry about 150 or 160 amps. And one of the things I want you to understand in this lecture today is why it can carry, what are the processes, what's the science behind this limiting 150 amps. Okay, so let's just have a quick look through the schedule for the next 2.5 days. Mark's completed the safety talk. There are just a few people who need to sign the relevant forms before they go into the labs. This is the lecture we're looking at the moment. Then we will go into the labs from about 11:30 till about 1 o'clock, and we're going to solder up some HDS samples, some high temperature superconducting samples or tapes in the labs, in the 4 labs. Then we'll have lunch, and then Charles will give a talk about cryogenics so that we can look at the technology and the importance of cryogenics in the context of superconductivity. Then we're going to go back to the labs for the rest of the afternoon until about 5 o'clock, and then you're free. And then tomorrow morning we'll kick off at 9 o'clock. Alex will give the talk on computational magnet design. We'll continue in the labs in the morning, and we'll split into 2 groups. One group will go into the labs, and one group will do computational work. And then in the afternoon we'll swap over, so that half of you will go into the labs, and the other half will again do computational work. So we're splitting you into two halves for these 2 sessions here, and then in the evening there's the tour at the cathedral and the dinner in the evening. And then on Wednesday we're going to kick off with some choices about either starting the poster that you need to produce as part of the outputs from this course, or going down to the labs and doing some additional IC measurements. And then we're going to finish off on Wednesday with the talk by Stuart taking us onto the large scale, so that you can see where the basic building block leads to in terms of the sorts of things that we need for superconducting materials. So Mark's already shown you the course demonstrators. This is where you're going to kick off by doing some measurements soldering some HDS samples up. The samples themselves that you will be provided with are very straightforward. They're HDS, well, very straightforward in the sense of that they just look as if they're a simple copper strip of material. So the outside of the tape is just this copper here, but there's a lot of development and technology that's gone into building what's inside the material. And inside the tape there's a hastelloy substrate, some buffer layers, and a high TC superconducting layer that's probably 1 or 2 microns thick, which is where all the current flows in this tape. So there are all these components here. I'm not going to talk about that in this lecture. Of course, you can ask any of the demonstrators or myself during the next 2 days about these these things here, but essentially sitting inside the copper on the outside of these tapes is a layer of superconducting material. And the thing to remember here is, although the copper, of course, and the other metals here are ductile, the superconducting material is an oxide, and that means it's a brittle material. So if you run the soldering iron into the tape, then you crack the superconducting layer, and of course it won't carry the current that it should. It will carry some current, but a current that's very different to the specified current for that tape. So this is the material that you're going to be given to solder up and do some measurements on. It looks something like this, where there's a copper layer around the outside, and all these layers here sit inside the tape. And this is the measurement that we hope you're going to do. This is not as beautiful as the one that I showed earlier, but in the end we want everyone here to have got to a point. We won't be able to put everyone's sample and measure everyone's individual sample, so amongst the teams you'll have to choose which of you thinks you've got a sample that's best soldered. That team will then put one of those samples onto the probe. You'll measure it, and this is the type of measurement that we hope we're going to end up with. So here's the voltage again along the y-axis, here's the current here along the x-axis, and you can see the baseline isn't quite flat in the way that the earlier data were, and we can talk about where these sorts of artifacts come from. But broadly, the current increases along the x-axis here, and eventually we get to some point where the voltage takes off. There's a lot of voltage generated across the superconductor. That means there's heat generated, and that gives us the critical current. Yes?
You might answer this later, but will we be, is that done using LabVIEW?
It is.
Will we be using that?
You will.
Okay.
On the graph, the voltage of the y-axis starts at -2 volts.
It does. So there are artifacts here associated with the gradient here, and the fact that it should be 0 volts here. And you will see when you do these measurements where a whole series of artifacts, including the fact that if you take an amplifier and just short it out, it won't give you 0 volts. So we're using the fact that we know that the superconductor has, we have to be aware that there will be an offset on the amplifiers in order to understand the data properly. Let me just say, in all of these talks, if at any point you want to ask a question, please just put your hand up. We can slow things down, and normally the question that somebody asks from the audience, other people are thinking to ask as well. So please be brave, put your hand up, ask the question if it's not clear. And this is textbook data, so yeah, this is at 0 volts here. Okay, I think this is the README that you should have read before you came. We've dealt with wearing the right sorts of things. We've talked about reading the health and safety documents. The documents to sign at registration are the two that are here on the front desk and the one for the meal. And then these are the outcomes. We want to do some, have fun, meet some new scientists, do some in-field IC, critical current measurements, and then we want to produce the poster. Does anyone have any questions about the structure of the talk, or how it's going to, structure of the 2.5 days, or how they work? Or, I think Mark has covered everything, actually. All right, so now we get to the second part, the important part of this talk here, and these are the questions that we're going to discuss at the end of this lecture. And all the lectures are structured this way. I know you've come across this before in the CDT. We'll give a short lecture, and then you should try to keep in mind these questions here as we make our way through the lecture, because these are the questions we need to try and answer. Some of these questions are straightforward. They're just extracting information from the lecture itself, and some of these involve some synthesis of the ideas in the lecture, and we'll see whether or not we can build a good understanding of what the critical current is in a superconducting material and why it has the value it has. So question that first arises is which industrial superconducting materials are there? And I should say that the discovery of superconducting materials has been entirely serendipitous. We don't really have a good theory that tells us where to find the next class of superconducting materials. I would say almost all of these materials were just the theory was added after the materials were discovered. There's the so-called low temperature superconductors that are the ones that are used in almost all the applications that are large scale at the moment. So of course CERN is made with low temperature superconductors, niobium titanium and niobium 3 tin. MRI scanners are made with niobium titanium. The levitating trains are niobium titanium. Fusion is the first large application that will use high temperature superconductors. And I think we're already rolling it out in terms of the research community, but in terms of industrial applications of HDS materials, there's still some where we're just in the infancy. So let's see if we can understand the most important materials. And as I say, there's no general pattern that we can look at to try and understand these. But it's useful if you can get some idea about why you might choose one material rather than another. Now, of all the materials that are here, the only material that's superconducting is niobium titanium. It's the only commercial it's the only material that's ductile. It's a low temperature superconductor, which is not ideal, but we don't have any high temperature superconductors that are ductile. This material here has an upper critical field of about 14 Tesla. And that means at 14 Tesla you kill the superconductivity. It passes from the superconducting state into the normal state. At 15 Tesla it's just a normal metal. There are no superconducting electrons inside the material by the time you get to about 15 Tesla. Which means that for most applications, most large-scale applications, niobium titanium, if you're going to operate below about 12 Tesla, niobium titanium is the material of choice. It's ductile. It doesn't matter if you drop the magnet. It doesn't matter if the magnet quenches. It doesn't matter if it sees some additional forces. The material will not fail in a brittle fashion. If you want to go above 12 Tesla or 14 Tesla, niobium titanium won't do the job for you because, of course, it's driven normal. And then you have to choose one of the brittle materials. And the material that's used in CERN is this niobium 3 tin. There are a few types of niobium 3 tin. It has an upper critical field of about 30 Tesla, which means that you can build magnets up to about 22 or 24 Tesla, something like that. If you want to build magnets that are higher field than that, then you have to go to the high temperature superconductors that have an upper critical field of more like 60 Tesla in the worst case. So at 60 Tesla, that means at 60 Tesla, the superelectrons are there until 60 Tesla, but above 60 Tesla, the superelectrons are destroyed and the material can't, even in principle, be used. However, we can only build superconducting magnets using the high temperature superconductors at fields. I'm not sure exactly what the record is, but probably up to about 30 Tesla or something of that order. Now, one of the things that you might ask, we've talked about, yeah.
On that last slide, why is that?
Sorry, why is?
Even though, like, theoretically it's 60, why can they go to 90?
So, one of the things that we know, of course, and that I'm trying to draw a distinction between, is the upper critical field, which is the field at which the superelectrons are destroyed and the material's no longer superconducting, and the critical current, which is what you're going to measure in the next couple of days, which is the maximum current that the superconductor can carry. Now, if you want to build a magnet, you need to put current through the superconducting magnet, and there's a practical limit to how big you can make the magnet. This means that to achieve a certain field, it's limited not by the upper critical field, but it's limited by the critical current rather than the upper critical field. So even though the material can remain superconducting up to, let's take niobium 3 tin, can remain superconducting up to 30 Tesla, actually, from a practical point of view, at 30 Tesla, it doesn't carry any current at all because it's not superconducting. So from a practical point of view, we can only make magnets that operate up to a half or 2/3 of the upper critical field.
Thank you.
So this is the plot of the current density that has been achieved in state-of-the-art materials versus the so this is the current density that's been achieved divided by the theoretical maximum, and on the x-axis here we've got the applied field divided by the upper critical field for that particular material. Okay, that's a lot to take in on a single overhead, but the thing to notice here is that this number here for most industrial high field superconductors, this is elemental niobium, so we can set this aside, that for most industrial superconductors we're achieving about 10 to the minus 2, that means 1% of the theoretical limit. So we're using superconductors in the MRI scanner down the road that's about 2 orders of magnitude, at a critical current density that's about 2 orders of magnitude less than the theoretical limit. If we could increase the critical current, if we could double the critical current, for example, we could halve the size of the magnet. Halving the size of the magnet would halve the cost for the magnet. So not only is the critical current the most important parameter from a technical point of view, but it's driven by cost. If we could understand the critical current properly, we could drive down the cost of magnets, and we're nowhere near the theoretical limit. We're 2 orders of magnitude lower than we could in principle be at. And you can imagine, if we were building bridges where we were operating at a stress that was 2 orders of magnitude lower than we are at the moment, we wouldn't be entirely happy with that. So there's a huge amount of headroom in superconductivity. Yeah.
Is the critical currents a function of temperature?
It is, and we're going to look at that. So it's a function of magnetic field and temperature and strain and irradiation. So we'll have a look at the properties. What determines the critical current? Why in the plot I showed could we only get to 140 amps? Why was it not 200 or 20? We'll try and understand the science of that, and then we'll see how it changes. Yeah.
Picking up on your offer to ask a stupid question. So functional materials aren't my area of expertise, but so I'm just looking at this and what you've just said, and elemental niobium seems to have properties that mean it's a good superconductor, and then you're just attenuating that by adding other, alloying with other elements. But yet previously you said we don't understand how it works, we don't know why it works, we have no idea where to look next, and I'm having trouble reconciling those two.
Yeah, no, I can understand that. That's the issue is that we're trying what superconductivity brings. So there's an old cliche if you work in materials: never compete with copper and never compete with silicon. So what superconductivity brings is access to very high magnetic fields. So if we look at the applications, if we look at body scanners, they're operating at 5 or 6 Tesla. In the Saclay case, up at 11.7 or 12 Tesla. If we're looking at accelerators, they want the highest fields that they can get at places like CERN. If you're looking at magnets, again, it's high fields, 5 Tesla, 7 Tesla. So we're looking to apply these materials to produce high magnetic fields. Niobium does work near its theoretical limit, but its upper critical field is about 0.2 Tesla. So it's not going to deliver high magnetic fields. So we have to turn to the high field superconductors in the applications where superconductivity is going to deliver. Okay. So in this part of the talk, we need to understand the critical current density. It's not a difficult property to understand, but let's just have a quick look. Now, I'm sure you've seen that there's a great deal of very beautiful basic physics trying to explain why materials are superconducting. And we can come up with these very beautiful phase diagrams and try and understand why materials are superconducting at a certain doping level, and try and understand where try and identify where we should sensibly look to find the next class of superconducting materials. But I'm going to completely set that aside for the purposes of this talk. We're not trying to understand why materials are superconducting. We're going to take the superconductors that we've got, the high field superconductors, and we're going to try and make them better for applications. We're going to try and make sure that we can use superconductivity in a way that means that we can build a fusion tokamak reliably, cheaply, so we can have fusion energy commercially. So we have to understand the basic properties of these industrial high field superconductors. There are two types of superconductor, and they're characterized by their magnetic properties. So this is a plot of the magnetization on the y-axis against the applied magnetic field. And the first type, shockingly called type 1, are almost all elemental superconductors. And if you apply a magnetic field, they're in this so-called Meissner state, which means that when you apply a field to these type 1 superconductors, a current is produced in the lowest energy state that stops the magnetic field from penetrating into the material. That's known as the Meissner state. And eventually, when you increase the applied field to a sufficiently high field, known as the thermodynamic critical field, you completely destroy the superconductivity. So there are only two states, the so-called Meissner state and the normal non-superconducting state, above this critical field here. Type 1 superconductors are all low-field superconductors like niobium. Most of the elements in the periodic table can be made superconducting, if not at ambient pressure, under pressure. And they just have these two states here. But this Meissner state only occurs at these relatively low fields. That is the state that is considered one of the two fundamental properties, along with zero resistance. But it's not the state that we need to understand in order to understand the applications of superconducting materials. We need to understand this mixed state here that occurs in type 2 superconductors. So in type 2 superconductors, again, as you apply the magnetic field, screening currents flow to stop the field getting into the superconductor. And that occurs for fields up to the so-called lower critical field, which is different for each of the different high field superconducting materials. As you go above the lower critical field and increase the applied field further, you get into this mixed state here. Eventually, you get to the upper critical field where the superconductivity is destroyed and there are no superelectrons, and you move into the normal state. All the high field superconductors are type 2 superconductors. All the important industrial materials are type 2 superconductors. And just to give you some idea about the numbers here, a typical number here is about 100 millitesla. So we don't need to worry about this. We're trying to operate at, say, 5 Tesla for an MRI, or we're trying to operate at 14 Tesla for fusion. The superconductor leaves the Meissner state very early up on as you increase the field. This is the field that matters. This is the field that for niobium Ti is about 15 Tesla, for niobium 3 tin is 30 Tesla, for the high TCs is 60 Tesla. And this is changing here from 100 millitesla to 60 Tesla. So all the action is in this region here in the mixed state. And this is the state we need to understand. And this is the important state that you're going to measure when you measure these tapes in the next few days. We can plot some beautiful curves of these critical fields. So for type 1 superconductors, there's only one critical line. We're in the Meissner state below this line here. This is the field versus temperature plot. We give this the name, the thermodynamic critical field. We give this the name, the critical temperature, and these are the two possible states. These more complicated type 2 superconductors are the ones that we're interested in. There is a Meissner state, but it's at very low fields. This upper critical field here, there is a Meissner state, and the lower critical field delineates the Meissner state from the mixed state. This is the upper critical field. This delineates the mixed superconducting state from the non-superconducting normal state, and this is the field that has the values of order Tesla or tens of Tesla. What's the nature of this mixed state? That's what we need to understand for this for these measurements. When we apply a magnetic field to a lump of copper or a lump of silver or gold, the field just penetrates essentially uniformly through the material. That's not what happens in a superconductor. If you apply a magnetic field to a superconductor, there are currents that flow around the surface of the superconductor, and inside the superconducting material itself, it forms a whole series of vortices. The magnetic field inside the superconductor is produced both by the applied field and the field produced by these supercurrents that are flowing around each of these vortices here. This is a very early experiment on niobium, which is a type 2 superconductor. If you spray a mist of magnetic material over the top of the surface of superconducting niobium, it doesn't just uniformly settle on the surface of the material. It's preferentially attracted to these vortices here. So when we're in the mixed state, the field penetrates into the superconductor, not in a uniform way, but in a way that has these vortices inside the superconductor.
Is this like Lenz's law?
The fact that the field is slightly lower in the superconductor than the applied field is a sort of Lenz's law, but this is a quantum mechanical effect. It says that when the field gets into the superconductor, it can't be uniform in the way that it is in copper or gold. It has to form these vortex structures when it penetrates into the superconducting material. Yeah.
Did you say that pure niobium, elemental niobium, is type 2 superconductor?
It is just type 2, yeah.
Okay. Did you say earlier that most type 1s are mostly like pure elemental? Is niobium like an exception then?
There are 3, I think. Niobium, molybdenum, and I've forgotten the third one that are type 2. But they're all low field superconductors. So we don't use any of the elements for high field applications. We have to use the industrial materials. Yeah.
So just to clarify, the induced field is negative because it acts in the opposite direction to the applied field.
Yeah.
Okay.
So we need a very clear distinction between the Meissner state, where the currents flow to stop the field getting in, that makes it strongly diamagnetic, and the mixed state, where in high fields the field inside the superconductor is slightly less than the applied field because of the supercurrents that are flowing. But the important thing about those supercurrents is that they form these vortices. They don't flow uniformly through the material. The field breaks down into these vortices that make this hexagonal structure. And that hexagonal structure occurs in all superconducting materials. So I showed you the very early work on niobium. There are the high field quasi-two-dimensional materials that again show these vortices in this hexagonal structure in this material here and in magnesium diboride and in this material. This looks more like a square structure, and there are some second order effects that give you that.
What are the length scales of these vortices structures? Is that roughly the size of the individual molecules, or is that more greater size?
So the length scale of the vortices, there are 2 length scales, and we'll come on to that in just a moment. So this is the length scales of a fluxon or a vortex. There are a number of different words that we use for these vortices. These vortices have their properties determined by quantum mechanics. So their flux is quantized. So we can call them fluxons, just as the charge is quantized in an electron or a proton. So this is sometimes called a fluxon or a vortex, and it's called a vortex because it has similarities with a tornado. So if you want to think about what each one of these vortices are like, there are 2 length scales. There's a length scale in a tornado which is associated with the density of the air. And then there's a length scale associated with the flow of the air around this tornado. And the same thing happens in a superconducting vortex. We've got a length scale associated with the density of superelectrons. That's of order a few tens of nanometers, to answer your question directly. And then there's a length scale associated with the current flow around each vortex. And that's more like a length scale of half a micron. So this is another way to think about the fluxon. this order parameter here is just a proxy for the density of superelectrons, and it drops to 0 or drops to something very small in the core of each of these fluxons. And the supercurrent flows around each of these fluxons, and the flux associated with this fluxon here is quantized, and is given by this value here. So this is the structure of these fluxons, and there's not time or good reason to go into the details of how we can derive the properties of these things, but essentially we just have to solve this free energy functional here. And this functional, it turns out, applies to all superconducting materials. So although we don't know why, or we suspect that different superconducting materials have different reasons or different microscopic explanations for why they're superconducting, once we try and understand their properties in field, which is important for applications, we can turn to this functional for all superconducting materials. And the reason that we can turn to this functional to describe all these superconducting materials in magnetic fields is because the energy terms here are extremely robust, very general terms. So all we have to do is minimize this free energy here. And if we can do that, we can understand the in-field properties and the vortex state, and we can look at all the details associated with the superconducting material. And let me just talk you through these three things here. This is the energy essentially associated with the condensation of the normal electrons into superelectrons. So clearly the superconducting state has the lowest energy, and we need to make sure that we choose these parameters alpha and beta properly. But once we've chosen them, they describe the condensation energy. This here is a very general expression from quantum mechanics. It's the canonical expression for kinetic energy. This is essentially a half mv squared here, or p squared over 2n, written using quantum mechanics. And then this here is the energy associated with the magnetic fields. So we're going to break this magnetic field inside the superconductor down into a whole series of vortices. And the question is, how many of these vortices are we going to get? And that's going to be driven essentially by this field term here. And then what we do is we spend our time minimizing this free energy here, and that gives us all the properties associated with the superconducting material. And Freddie's looking at me in absolute horror as I sum up a lot of the work he'll have to do in just 30 seconds or a minute. But that's his job, essentially, to look at this free energy functional here and try to consider geometrical complexity, and we'll have a look at geometrical complexity a little later on. And pin, yeah.
What are superelectrons?
What are superelectrons? So when we talk about superconducting materials, they're all conductors. So we take something like copper or gold or silver. These are metals with conducting electrons, and those conducting electrons scatter if we want to think about the resistivity or electrical conductivity of a metal, we know that those electrons scatter and produce heat. So that if we put a current through copper, we generate heat. Now, when a material becomes superconducting, those electrons pair up in a special way that is different for different types of superconductor. And there are many different theories, so I'm just going to give you one of them. They pair up to form a boson. And that means that they're sort of glued together in a way that means that they don't scatter anymore as they make their way along the material. And we call those paired electrons superelectrons. They're known as a Cooper pair after the person who first came up with this idea. And the beautiful property they have is that they don't scatter, and that's where the zero resistance comes from. Yeah.
So, coming to that, and in like a tape, in the Meisen state, are those pairs just going like just in a straight line, and in a mixed state they're going around those vortices?
Okay. So, in the direction that the superelectrons travel in is determined by the external conditions. So if I take a superconductor and I just cool it down, pull it down to liquid nitrogen temperatures. Just take the reco you're going to look at. Cool it down. The superelectrons pair up and they travel in all directions, which means that there's no magnetic field produced by the material itself. Now, if I apply a magnetic field, and we're in the Meissner state, the superelectrons, in a way that quantum mechanics requires, screen out that magnetic field, so they flow around the outer surface of the superconductor. If I increase the field further, the field gets into the superconductor because we're no longer in the Meissner state. Under those circumstances, when the field gets in, now the superelectrons have to flow around and produce all of the fluxons in the system. So there's now a whole series of vortices that have penetrated into the superconductor. There's magnetic field in the superconductor, and the superelectrons are both flowing around the surface to try and reduce the field slightly from the applied field, and they're flowing around each of the vortices inside the material.
Thank you.
All right, that's the so-called time-independent Ginzburg-Landau theory, and then we can make things more complicated and move to time-dependent Ginzburg-Landau theory, and that's what we need in order to understand what's going on. So let me just give a visualization of what goes on in the superconducting material. This is the plot of the magnetization on this axis here versus the applied field. In low fields, we're in the Meissner state, so the field is completely excluded from the superconductor. But over most of the field range, and even this is only is not really representative of a very high field the industrially important superconductors, as this ratio looks more like 2000 or something like this. But in all cases, we have the Meissner state first at very low fields, and then the field penetrates into the superconductor. We're in the mixed state, there are vortices inside the material, and this is the reversible magnetic response of a superconductor. And I just want you to visualize that. So if we increase the field, at low fields we're in the Meissner state, and there's just supercurrent that flows around the outside and stops the field getting into the superconductor. And then we increase the field from here to where this red dot here is. So we're now at a field that's higher than the Meissner state. There's still a current that's flowing around the outside, but this is the special properties of superconductors, and it's the mixed state that we need to understand the critical current measurement properly. The field now penetrates into the superconductor, but it doesn't penetrate in a uniform way. The field penetrates in these vortices here, where there's a superposition of a screening current around the outside and vortices that are in the core of the material. Now, because this material has what's known as pinning at the surface here, and because it's not infinitely large, we don't see the hexagonal structure that we saw in the experiments earlier on. And we can increase the field yet further. So now we've increased the field up to here, and now you can start seeing the hexagonal structure. That there's so many of these fluxons now that you can see they form inside the superconductor. The screening current flows around the outside, and you can see that most of the vortices have 6 neighbours that surround them, 6 nearest neighbours, in the hexagonal or triangular structure. That's increasing the field in this case to 0.4 of the upper critical field. Then if we go up to 0.7 times the upper critical field, we don't change the field of the fluxon, because a bit like, it's a quantum mechanical entity, this quantized flux. If we increase the field, we just put more fluxons into the superconducting material. So as we go up to 0.7 BC2, or 0.7 times the upper critical field, we get more fluxons, and you can really see the hexagonal structure. Then if you go up to 0.9, the fluxons overlap each other, and eventually, if we get to the upper critical field, we then destroy the superconductivity. There are no superelectrons in the system, there are no vortices in the system, it just behaves like copper or gold, or any other metal. And the field just uniformly penetrates the material. Then if we reduce the magnetic field, in this case down to half BC2, the fluxons renucleate, many of them leave the superconductor as you reduce the magnetic field, and we get this structure here. And then as we reduce the field back to 0, there are some fluxons that are trapped by the pinning associated with this interface here. That means that we don't get a reversible magnetisation in this case here because of the pinning at this surface here, and it's pinning that we need to understand in this course. Now, of course, there's some complicated laminar and turbulent flow associated with these vortices at the spiralling in from the edge of the superconductor into the material. And this is the classic laminar turbulent flow where we start off in the Meissner state with laminar flow, and then as we increase the magnetic field we cross over to turbulent flow, and the vortices, the superconducting tornadoes if you like, get produced at the edge here and then spiral into the spin into the material. Okay, so we've got the basic properties of superconductors. We understand that type 2 all the important high field superconductors are type 2, and we need to understand the mixed state and the fluxons penetrating into the superconductor in high fields.
Yeah, sorry, if you just go back 2 slides. The graph there, that behaviour, is that independent of how quickly you kind of ramp up and ramp down?
No, it isn't actually. No, it's not independent.
Over what time scale is that? And then how quickly or slowly you do it affects your characteristic?
I'm going to keep things simple, and I'm going to say that if we look at MRI body scanners, you know that if you wheel somebody into a body scanner and wheeled it out, the field has to be very uniform and it has to be very stable. So the critical current that's flowing in a superconductor inside a body scanner changes about 1 part in 10 to the 9 per year. So it does change as a function of time, but it's an extremely small amount. They talk about, they convert them to proton frequency, which I'm not going to bore you with, typically 400 megahertz. So you may have a 400 megahertz MRI scanner, and typically they may change by 1 hertz in a year. So that gives you, 10 to the 1 part in 10 to the 9 or something like that. So it is a function of time, but we can also find that these things are very stable under the first order. They're very stable. Okay, we've understood the basic properties of superconductors. Now we have to understand the pinning inside a superconductor, and this is a simplification of what goes on in a superconducting material. We can add a defect here, and this fluxon will now preferentially want to sit on this defect. It will lower its energy by sitting on the defect, and the reason for that is at the core of the fluxon there are no superelectrons, and there are less superelectrons inside this pinning site here, and so one would like this one finds and one expects that this fluxon here is going to it will lower its energy if it sits here. Now, if we apply a current to this material, we're going to apply a net force on these fluxons. So if I apply a magnetic field to a superconductor, the fluxons penetrate into the superconductor, and then I put a transport current through the superconductor, which is what you're going to do in your measurement. When you apply a current to a superconducting material, there's a net force on the fluxons. If your superconductor were a perfect single crystal, the fluxons would move and they would generate heat, which means that although the material would be superconducting, there are superelectrons in it, it would be useless from a technological point of view, because as soon as you put a current through it, the voltage would increase, you'd generate heat, and we couldn't use it as a superconductor. So from a practical point of view, when we're trying to understand the critical current density, the maximum lossless current, in practice what that means is that we have to hold these fluxons and stop them moving when we put a current through a superconducting material. This is just the experiment that you will have heard about when you were an undergraduate, where if you fire electrons, a beam of electrons into a magnetic field, you know there's a Lorentz force on them, and the electrons will change direction as they move through the magnetic field. This is the equivalent, where what you're doing is you're holding the current that's flowing inside the superconductor, and now it's the field that's moving rather than the charges that are moving. The current that you're putting through the superconductor can't leave the superconductor. But there ends up being a force on these fluxons associated, a Lorentz force associated with a transport current flowing through the superconducting material. If the fluxons move, Maxwell's equations tell us that they generate an electric field. They generate heat. So the maximum current that a superconductor can carry is determined by the point at which the fluxons are ripped out of these pinning sites and move across the superconductor, because that's when we then generate the voltage. Okay, so this is a very simple form of pinning where you could reasonably say, well, all we're going to do is put a lot of second phase material or defects into the superconductor, and that will increase the current density from 0 to some value, and the more material that we can put into the superconductor, non-superconducting material or dirt that we can put in the superconductor, will help us increase the current density that this superconductor can carry. So it comes about because of this pinning comes about because of the Lorentz force on the fluxons. We need to stop them moving under this Lorentz force, and we can pin them with defects of almost any description, non-superconducting material, where the fluxon prefers to sit on the defect because it lowers its energy. Now, in practice, we often parameterize this current density using this pinning curve here. This is the volume pinning force, which is defined as the critical current density times the field. This is a force per unit volume. And we just describe it mathematically with this equation here. It's essentially a useful empirical magnet designer's equation. We can try to justify it theoretically, but the justification is rather weak. If we look at the important commercial materials, niobium titanium has these values 1 and 1 here, niobium 3 tin, 0.5 and 2 here, and for Rebco we get about 0.5 for this value here, and this number's probably about 2.5, something like that. Yeah.
If we give it enough time while demagnetizing it, would it not actually end up going to 0? Would the pinning force not eventually overcome the Lorentz force? Rather than just shutting it off right away.
So if I don't put any transport current through this superconductor, the fluxons are going to migrate and preferentially sit on these pinning sites here. And then I put a current through the superconductor, and that puts a force on these fluxons that are now pinned on this pinning site. And at the beginning, the pinning from the pinning site holds the fluxon in place, and the additional Lorentz force is sufficiently small because the transport current's small, but it doesn't move. And if it doesn't move, that means the voltage across the superconductor is 0. Its resistance is 0. Then as I increase the current through the superconductor, eventually Lorentz force on the fluxon is sufficiently large that it rips it off the pinning site. Now it's moving, and if it's moving, it generates heat and it generates voltage.
That's when it becomes a superconductor, right?
No. So when we talk about it becoming a superconductor, we need to be very clear about the definitions of the words we're using. If there are superelectrons inside the material, it is a superconductor. Okay? But if I put a current through such a superconductor in the mixed state, and there's no pinning, the fluxons will just move through the superconductor. It will still be superconducting because it's full of superelectrons, but it doesn't carry any current. It's useless from an applications point of view. So in this case here, it's always superconducting because there are superelectrons everywhere. What we're now talking about is when you do a critical current measurement and you measure the voltage as a function of current. At low currents, it remains 0 resistance. Eventually, when the current's large enough, the Lorentz force is large enough to rip the fluxons out of the pinning site. And now we generate a voltage and it's resistive. Still a superconductor. Just a resistive superconductor. It's a superconductor because there are superelectrons. but it's resistive. It's of no value from an applications point of view because it's generating a lot of heat. Any other questions? Questions are good. Yeah.
I think you basically answered my question there, but my question was going to be that my understanding of what defines a superconductor is that you can observe the Meissner effect and that it has zero resistivity, or zero resistance, or whatever. And so, if with the type 2 superconductors you have a large mixed region, which is basically the bit that you care about for applications,
Yeah.
where you're no longer getting the Meissner effect,
Yeah.
is the resistance still zero? And so I'm guessing from what you just said there, my understanding is that it is for some of it.
It is. If you have no pinning, it is zero, yeah. The resistance is not zero.
If you've got no pinning.
If you've got no pinning. If you have a perfect single crystal of superconductor, at very low fields, you're in the Meissner state. There's no field inside it. It's a superconductor. In high magnetic fields, you're in the mixed state. If there's no pinning and I put a current through it, the fluxons move because they're not pinned. It's still a superconductor because there are super electrons there with an energy gap and a specific heat jump and all the properties that we know about for superconducting materials. But it's resistive from origin. In other words, as soon as you put a current in, it's just going to move the fluxons, that's going to generate heat. So it won't have zero resistance in the way that you mentioned, but it is a superconductor because there's super electrons in it. We need a slightly deeper understanding of what a superconductor is in this case.
Thank you.
In terms of engineering these materials, how much effort then goes into designing the density types, whatever, of defects within the material? Presumably a huge amount.
A huge amount, because that's where the whole game is. You can make perfect single crystals. They don't carry any current. Because the fluxons move as soon as you put a current into them. What we're interested in doing is making a magnet. And making a magnet means having a current density that's flowing in high magnetic fields. So the whole game, in terms of the development of these materials, once the materials have been discovered, is how do we increase the critical current density of these materials? How do we put more pinning sites in to push this current density up? And as I mentioned, this is not a small matter technologically. If we double the critical current density, then we can halve the amount of material that we need to make the magnet, and that halves the cost. And there's a huge headroom.
If we increase the number of pinning sites indefinitely, won't that allow fluxons to jump between pinning sites? And
It will. It's going to get complicated, I'm afraid. So you, in order to do the measurements in the next couple of days, you need to understand what pinning is and realise that a perfect single crystal is of no value for a high field application. The way we get current through these materials is by introducing pinning, and we're going to see some of the theoretical calculations that show us how the pinning works and the sort of complexity that you're alluding to. You need to understand the basic idea about why we end up with any pinning at all. Why do we get any current density at all? Why was that 140 amps and not 1,000 amps? And it's basically determined by the amount of pinning that we have in the material in the very general sense.
You speak about fluxons flowing under the
Yeah.
what's the order of magnitude is defined by the critical heat that stores in superconductor.
So Alex will talk about this tomorrow morning in terms of magnets quenching, thermal runaway and things like this. The heat is very simple. It's always I squared R, or so it's proportional to the voltage. So if we have a VI trace and the voltage takes off, if the voltage takes off, then it's V squared over R, and that's the amount of heat that's generated. So it's different for different materials. It does depend on the pinning and so on. But essentially all superconducting magnets operate below the critical current. The critical current is the that you're going to measure, is the technologically important parameter. There are materials in ITER, if it gets built and run, they will run above the critical current density because some of the strands in ITER are damaged. So they will be running in that regime. But to first order, the MRI scanner down the road runs below the critical current density or at the critical current density. All right, so now we can think about this measurement here in terms of the fluxons and what's going on. We increase the current, there's a force on the fluxons, but the fluxons are held by the pinning sites. As we increase the current yet further, the force on the fluxons increases. The Lorentz force on the fluxon increases as we increase the current through the superconductor, but the pinning sites are still strong enough to stop the fluxons from moving. And then we get to the critical current density here, and now the force on the fluxons from the transport current is sufficiently large to rip them out of the pinning site. Now as they move, we generate an electric field or a voltage along here. And this is the critical process here. Here the fluxons don't move. Here the fluxons do move, and they generate a voltage and a heat. Now, when it comes to measuring superconducting materials, we did a whole series of measurements here in Durham for ITER to make sure that the materials that go into the magnets or have gone into the magnets meet the specs. So this tells you what the important parameters are when you make a superconducting material. And you can see we've got to get the chromium plating on the outside of the wire right, and we've got to get the copper non-copper ratio and the diameter of the wire right, and the twist pitch associated with the filaments right, and we've got to get the purity of the copper to be right, and we've got to get the magnetic hysteresis. Alex will cover some of this tomorrow, and we've got to get the current right. And if the material doesn't carry the current, it's useless from the point of view of making the magnet. So we need to make sure that these superconducting materials carry this current, and we need a good idea about what critical current is.
Just to confirm, practically once the just below critical currents, right?
Yeah, that's where we operate. Yeah, just below the critical current. I want to add in a caveat. For fusion applications, we operate just below the critical current. For MRI applications, we operate about 60% of critical current, something like that.
Is there a reason?
Yes, it's to do with it's to do with the very high. So one of the things that you guys will probably address if you stay in fusion is that we have developed all the low TC materials for the body scanner community. We know that there's this industrial community. We want body scanners. We want to make them cheaper. We want to roll them out we want to make them as cheap as possible. And the materials have been superconducting materials have been optimized for that particular application. That's not the same as optimizing them for fusion. And we will change if we're smart. The economics will drive it. We will change the way we design superconducting materials, the way we manufacture them. For fusion eventually. Okay, this is just a list of the measurements that we did for ITER, and I'm very happy to chat about that, but I don't think I'm aware of the time moving on. So we've talked about the industrial materials. We've talked about niobium titanium, which is the only ductile high field superconductor, running out at about, it's this one here, running out at about 15 Tesla. Current density dropping to 0 there, the upper critical field being a little bit higher than that. We've talked about niobium 3 tin, which was the superconductor used in the CERN. Upper critical field about 30 Tesla, current density dropping to 0 at about 25 Tesla. Now, in fact, a magnet, if you want to think about the sort of numbers that we need in a magnet, you need about 1,000 amps per square millimetre. This is an engineering number that you might stick in your head, between 100 and 1,000 amps per square millimetre as the current density you need in a wire to build a magnet of a reasonable size. You could say, well, why isn't 5 amps per square millimetre okay? It is, but you'd end up with a huge magnet, and it would cost an absolute fortune. So typically they operate in that sort of regime. Now, let me just talk you through the important industrial superconductors. This is the one that we don't talk about very much in fusion. I think that's a mistake, actually, but anyway. It's a low temperature superconductor. It's the only useful ductile superconductor. TC is 9 Kelvin, so obviously low temperature. VC2 at 0 temperature of about 14 Tesla. So if you think about those phase diagrams that I talked about, that's where we are in terms of field. If you want to go above about 12 Tesla with niobium tie, then you can use niobium 3 tin. There's a number of different ways of making it. You have to make multifilamentary wires. I haven't really talked about that at all. We've just talked about the superconductor. We're only starting the development of multifilamentary HDS materials. But if you want to go above 14 Tesla, which we do in accelerators and we do in ITER, then you have to use niobium 3 tin. I was going to show something on the cables, but one of the things you might do is if you find you're doing your experiment and you want a break, we've got a display outside of the labs, and you can ask one of the demonstrators to show you the display, which has got these cables that they're going to use in ITER, and it's worth taking 15 minutes out just to go and have a look at this display in one of the corridors. Just ask one of the demonstrators about that. All right, so I'm going to get back now to the question that I was asked before about, doesn't this all get complicated very quickly? And it does. But I don't think you need to understand that. I think that if you understand, the important message to take from this lecture is the idea of the mixed state being specific to superconducting materials, where the field penetrates in as these fluxons, and the critical current delineates that region where the Lorentz force on the fluxons is sufficiently low that the fluxons remain stationary. The critical current above that, the current is sufficiently large that the Lorentz force rips the fluxons out of the pinning sites and generates the electric field or the voltage. So this is a polycrystalline, a description of a polycrystalline superconductor. And just to show you how this is a two-dimensional slice across a theoretical model of a two-dimensional superconductor. I can do this. So you can see that, it's quite difficult to see, but we've got some other ones as well. You can see that what actually happens in this material, when we talk about pinning, in a polycrystalline material, of course, the grain boundaries have got a much lower, much weaker superconductivity than the grains. So here are the grains here. We've gone to a sufficiently high field that we're in the mixed state. So these are the fluxons. They don't look very hexagonal to me because this grain, the boundary of the grains is there aren't many fluxons inside the grains. And we've gone to a current that's above the critical current. And if you look very carefully, you can see that these black dots here, which are the cores of the fluxons that sit inside the grains, that as we go above the critical current, this is not, that as we go, yeah, maybe you can, I don't know if you can you see these fluxons sliding along these grain boundaries here? It's quite difficult to see it, but it gives you an idea about the sort of different types of pinning you can get. I've talked about ripping fluxons out of pinning sites, which is fine if it's an isolated pinning site. But in a polycrystalline material, we've got these grain boundaries that run across and along the whole of the material. And in the case of the polycrystalline materials, the fluxons are not ripped out of the grain boundaries. They slide from one side of the superconductor along the grain boundaries to the other. And there's a whole class of fluxons, or group of fluxons, that are not moving at all when we're above the critical current density. So they don't all behave in the same way. Let's see if we can do this one here. Yeah, so this is another visualization of that, produced by Alex, actually, who's going to talk tomorrow. And you can see that this is the polycrystalline material. And you can see that the fluxons in this case, there are some that are inside the grains, but the grain boundaries are sufficiently dense that most of the fluxons, when they're moving, are sliding along the grain boundary. We still talk about this as pinning because G. Hughes, back in the 80s, introduced this language of pinning. And we think about fluxons as being pulled out pinning sites, and if you go to a lot of the talks about pinning, they're basically they're often thinking about that. But this is what the TPL tells us is really going on in a polycrystalline material. You can see the fluxons are sliding along the grain boundaries. But the basic mechanism, what you're going to do in the measurement, is still the same. Below the critical current density, there are no fluxons moving. Above the critical current density, if the current's higher than the critical density, the voltage takes off, and at least some of the fluxons are necessarily moving through the material. Now, in the high TC materials, they put in a whole series of defects. They can be isolated spherical defects, they can be standard defects in the crystal structure, or they can be these rods. And this has been produced by Charles, who's sitting at the back, hiding at this stage, but you can ask him about these calculations. So these are the rods with the weaker superconductivity. This is the dirt, if you like, that they put into the Repco that you're going to measure. And these, and then as you go above the critical current density, the fluxons now pull away from the rods, but of course they're not. These fluxons are also flexible, so they don't just pull away as rods across the superconductor. They pull away in some part of the pinning site, and then they essentially a dislocation in the flux line lattice runs through the whole thing. Okay.
Can they tear?
Sorry?
Can fluxons tear?
Can they tear?
Or like lose the structure?
Well, they're quantized, so you've got to be. There are constraints on the flux has to be quantized at all points. Quantized means that the current, so in quantum mechanics, of course, we quantize a whole series of properties. So the structure of the periodic table comes about because we think about the electrons having a quantized angular momentum as they travel around a nucleus. That quantization is critical to it's why we have the structure of the periodic table as it is. So we can talk about quantized angular momentum. And with the fluxons, we've got the same thing. We've got a quantized magnetic flux, which is the magnetic field. Another way to think about that is it's a constraint on the angular momentum of the current, the supercurrent that flows around a fluxon. So there are some constraints. We'd have to define what tear meant. But now, of course, these pinning sites and the properties of superconductors change as a function of field. Yeah.
I'm sorry, this may be quite an obvious question.
No,
Is fluxon movement through the grain boundaries, does that make the material useless? Like, does that mean that there's resistance?
it means that there's resistance. Once the fluxons move,
Yeah.
it generates a voltage. So when you're doing the measurement, if the voltage isn't zero or plus or minus some artifact, if it isn't zero, then the fluxons are moving and you'll generate a voltage.
Okay, sure. But then, so why is there so much, like, why do we care about what's going on in the grains then? If the first movement of fluxons seems to always be along grain boundaries initially.
Yeah, we need to control the grains and the grain boundaries.
Okay.
If we could, the problem is that the fluxons have got a core that's a few tens of nanometers or a few nanometers. The grain boundaries are a few nanometers. And empirically what we've found is if we don't put grain boundaries into a material, or introducing grain boundaries is one of the ways of putting pinning in. And that was the way that we increased JC in niobium 3 tin. What we would like to do is have control of the grain boundaries at the atomic level, but we don't have that at the moment. We're a long way from anything like that. It's the same problem with solar cells. We just don't have control over grain boundaries yet. In science, we spend a lot of time thinking about perfect single crystals. And actually, in terms of many applications, we need to understand in a much better way what's going on in a grain boundary, how we could manipulate it, how we could make it more resistive or less resistive, how we could make it narrower. Okay, so we can change this critical current density here. We can change it by changing the temperature, because that will change the strength of the superconductivity. We can change the magnetic field, that will change a number of fluxons inside the material. We can also change the strain on the superconductor. If we strain the structure, we're going to change the upper critical field, and that's going to change the properties of the superconductor. we've done a lot of measurements in Durham on understanding the critical current of superconductors under strain. So there's historically there's a huge amount of looking at the critical current density as a function of field. So if I look at this plot here, for example, this is 5 Tesla, this is the 23 Tesla. We're measuring the current density as a function of strain at different fields. Here at 4 Kelvin, 8 Kelvin, 12 Kelvin. So field, temperature and strain change the critical current of a superconductor, and that's true for low TCs and high TCs. This is the equivalent data. We don't need to look at it in too much detail. We also need to be able to make joints in superconducting materials, and that's it. So I like to put this on at the end because there was a time when, well, I think a number of people now are talking about fusion as being, fusion has changed a huge amount from being a very important Cold War experiment, which is what ITER was set up for. You know, Gorbachev and Reagan got together and came up with ITER and managed it as a sort of Cold War project. It wasn't seen as an important technological field in the way that we now understand it is, and that we really need to look at trying to make fusion work for very obvious global warming, global heating reasons. So I hope you've got an idea of the basic building block that you're going to look at in the measurements that you do in the labs over the next couple of days, and that you've got a good feeling for what critical current is and what's going on at the microscopic level inside the superconductor when you make a critical current measurement. Cryogenics is part of the enabling technology. If we don't have good cryogenics and we don't do that properly, we don't have a superconducting system. This is done so well that superconductors are cheaper than, for high fields, are cheaper than copper. Alex is going to talk about some of the computational magnet design when you split into two halves, half in the labs because you'll be using the high fields at that point, and half doing computational magnet design. And then Stuart's going to show how we take these building blocks here and end up with cables and magnets. And there's a whole nother challenge in the engineering of taking these building blocks and making a real tokamak. Okay, great, thanks very much. We'll stop there.